This is Mr. Baker, and these are the exponents and exponentials problems we're reviewing for the Tennessee End of Course test. Mostly we're dealing with the different properties and different versions of our exponential growth equation. This first one is technically designed to be a properties of exponents problem, but really the word that should catch our attention here is the word equivalent, and we've seen that come up before. And in multiple choice problems, there's an easy trick to work with equivalent, and that's pick a number, plug it in for the variable in the problem, and in all the answers, see which one gives us the same value. And my favorite number to plug in for that is 7. So let's plug in a 7 for that A. 24 times 2 to the 7 plus 5 power. Be careful. You may need parentheses around that exponent when you're typing it in the calculator. It's always a safe practice to do that. But that's going to give us 98,304. Well, now let's plug in 7 to all these multiple choice answers, because if they're equivalent, plugging in the same number for A will give us the same output number. Plug in all those 7s, and that's going to give us all those numbers. One of them is the same, and that is B. That one must be the one I'm looking for. Anytime we're dealing with equivalent and multiple choice, that can be a really good technique to use. But how is it really designed to be done? That wasn't how they designed this problem. What they really wanted us to do was to change this problem into this answer. Well, the way to do that is take that 24 and factor it down into its primes. So we'll take that problem, break up 24 to be 3 times 2 times 2 times 2, because 24 is 3 times 8, 8 is 2 times 2 times 2, and then still times 2 to the a plus 5 power. Well, now we've got a whole bunch of 2's. Look at all 3 of those 2's. They can go with these 2's. 3 2's there, that's 2 to the 3rd power. And when you multiply powers with the same base, what do we do with their exponents? We add the exponents. So let's add those exponents. That's 2 to the a plus 5 plus another 3. Still have that 3 on the front. But now my exponent is a plus 8. That's how the problem was designed to be done. But because they were looking for something equivalent, we had a quicker, well, probably a slower technique, but it certainly worked. All right, here's another problem that has us looking for equivalent expressions, but we're not doing a multiple choice problem. So just plugging in 7 for M wouldn't be helpful. Once I have the problems written, it might help. Let me check my answers. Plug in 7 here and then 7 in the answers that I wrote, make sure they give me the same value. But it's not going to tell me what the answers are, so I'm going to have to think about it. What I'm really doing here, write an expression equivalent to m to the 5th that includes a fraction. I'm writing a problem. And most likely this fraction is going to be a fraction with some m's in it. So we got a fraction with some m's in it. If I've got m's in the top and bottom, I'm actually dividing. When you divide powers with the same base, what do you do with their exponents? You subtract their exponents. So right now, this is m to the 1 minus 1. 1 minus 1 is 0. That's not going to help. I want them to subtract to be 5. So let's get a little bit bigger, at least on the top. If I have 6 on the top, m to the 6th, 6 minus 1, that will give me m to the 5th. So sometimes that's how you have to do a problem like this. You have to play with it a little bit, get the wrong answer, or start building it and see what you have to tweak along the way. We made a fraction, we put some m's in it, we thought about, hey, when I divide, I subtract the exponents, then I made sure I put in the exponents it would subtract. And there's a lot of different ways to do that. 6 minus 1 sure works, but so does 7 minus 2, 8 minus 3. I do remember seeing some people with answers that were m to the negative 5 with a 1 over it. And we'll talk about that when we get to the negative exponents one in a second. But that one technically works fine. So let's look at the negative exponents. Let's just start with m with a negative power. I didn't start with negative 5. I started with negative 3 because I knew m to the negative 5 wasn't equal to m to the 5. So I just started with some negative exponent. It's way too low. I don't want negative 3. I want positive 5. I'm going to need to add to negative 3 to get it to m to the positive 5. When do I add exponents? Well, when I multiply. So let's multiply by some m's. That's not going to do it. Let's throw in an exponent on that m. What if it was a 5? Is that going to do it? Well, I would add the exponents. 5 plus negative 3. That's only 2. I'm too low. I'm 3 too low. So let's move that up a little bit. There we go. Negative 3 plus 8. That will give me m to the 5th power. By the way, remember that a negative exponent really does mean 1 over that power. So 1 over m to the 3rd power is what m to the negative 3 power really means. So why did this 1 over m to the negative 5 work? Well, 1 over m to the negative 5, which would also work on this answer because that has a negative. The negative exponent means that I'm actually going to bring it to the top because it's already in the bottom. So that would be equal to m to the positive 5. So that would work too. All right. How about a radical? Well, that's a radical, a square root. It could be a cube root or a 4th root or a 5th root, but a square root is probably the easiest one. And I think of it this way. If I wanted to equal m to the 5th, that's like I want to have m to the 5th pulled out. That's what I want to pull out of the square root. If I want to pull just one m out, how many m's do I have to have inside the square root to get one m on the outside? Well, I have to have 2. 2 on the inside gives me 1 on the outside. So if I want to get 5 m's on the outside, how many m's need to be inside? Well, I need another 5 m's to match up with the 5 m's I'm going for. I need 10 m's inside. And either one of these would technically be a fine way to write it. M to the 5th times another m to the 5th. That's 2m to the 5ths inside to give me an m to the 5th outside. Or to say, hey, I've got 10 m's inside, which would give me half of that, 5 m's on the outside. There's certainly other ways to do radicals, but that's probably going to be the easiest. The square root's the easiest of the radicals. We could have done quite a few other things, really. M to the 4th times the square root of just m squared. That would do it. That would just pull one more m out. So there's a lot of things we could do. This would be the first one I would have thought of. So that's why it's the one that we've got popping up here. So how about only exponents greater than 5? Well, let's look at the answers we have. That's an exponent greater than 5, but that one's not. 8 again, but negative 3 is not. But what about this one? That answer, can I just use that again? It's only exponents greater than 5. And the 10's the only exponent I've got. That could work. But that one feels like it's cheating a little bit. It's perfectly fine. It fits the directions. But probably the first thing I would think of is just to use bigger numbers in a fraction. So I could subtract the exponents and still get them to equal 5. So maybe if I started with m to the 19th, that's a lot bigger than 5. What would I have to subtract from 19 to get 5? Well, 19 minus 14, that would do it. Or any big exponent that I wanted to start with on top, I could figure out what to be on the bottom. So, and there's a lot of other ways they could ask this same kind of question. I've seen questions like this pop up on the practice material from the state. So this definitely seemed like a good problem to look at. And it's also a good refresher for our rules of exponents. Keneal is working on free throws. Now, we're writing an equation to go with that, and if you look down here, it definitely looks like it's going to be an exponential equation. which means it's probably going to follow pretty well along the form of our exponential growth formula. Remember that arg is sometimes over n, and we have an n up there with a t, but that's when we're doing compound interest. This isn't money, so we're definitely not working with an n. But with Keneal's free throws, this should work out for us okay. With the same idea, we are going to replace the 1 plus r with a growth factor. And we've talked about that before because instead of increasing by a certain percent, we're just going to keep multiplying by a number over and over and over again. So, but let's start with that first number. That's that P. What does P stand for? That's for principal, which is our starting amount. What's the starting amount of free throws that Keneal makes? Or he's attempting 10 of them, so 10 is that starting amount for us. Now, he's not going to do 10 every day. He's going to do, we're going to apply a growth factor to that. And what's our growth factor? Twice as many. Twice means 2 times. So we're going to keep taking that 10 and multiplying it by 2, and then that 20, multiply it by 2, multiply by 2. When you multiply over and over again, that's going to be the base of an exponential, whatever you keep multiplying by over and over. So that's a 2. That's what we keep multiplying by. So 10 times 2 to the whatever our exponent is, and that's going to be whatever the number of days is. So that's going to be our time, that's day x. Because it's whatever day x is. So 10 times 2 to the x power. And I really like this as an answer, but it might not be the answer they're looking for. It might be. Honestly, this is a bigger problem on a multiple choice question than anything else. The reason for that is this is the formula that would work if we start on day 0. And a lot of the times when you're counting things, your starting time is time 0. But with numbers of days especially, if we try to check that out with that equation, we know on the first day he should be taking 10 shots. But if you plug that in, 10 times 2 to the 1, that's 20. First day isn't supposed to be 20 shots, it's supposed to be 10 shots. There are ways to fix that. Sometimes you'll see that exponent changed around to make it an x minus 1 exponent. Other times, and my favorite thing to do is that 0. But the other thing to do to fix it is to go ahead and, yeah, the 2 is going to be the same, yeah, the x is going to be the same, but let's change that starting number. What would that number have to be in order for it to be multiplied by 2 to the 1 and get 10? Well, that number would have to be 5. So I could make that 5 times 2 to the x power, and that would work for the first day, second day, and I don't have to worry about making a day 0. Now, which one is right? Really, if this was the way the problem was worded, either one should be acceptable because it doesn't specify if you start on day 1 or day 0. The way I read it, maybe they wanted you to start on day 1, so maybe the second one's a little better, but both of them do work, and there can be an argument for both solutions. This one definitely fits our experiences with exponential equations better. This one maybe fits the wording better. So if you're doing a multiple choice problem and you don't see this answer, then maybe the second one's the one to go with. If you see both, I think I lean more toward the second one. For me on a test, for this wording, I would have accepted either one. And you know, they do have different teachers, not me, who actually do get to help decide what are acceptable answers. And I think either one of these would be accepted if it was a free response problem. This one's another application of that future value equation. This one actually gives us the equation right in the middle of the problem. They like to do that, give you a paragraph with an equation buried in it that asks you something about the equation. This one has us figuring out which statement describes the population. 80% increase 80% decrease, 20% decrease, 20% increase. So we can eliminate half of those if we can decide if this is an increase or a decrease. And we can figure that out. We don't care how many B's she starts with, that's the 1,000. It's that 0.80 that's going to tell me a lot more. And since that is less than 1, that means this is exponential decay. This is actually decreasing. So anything that says increase is the wrong answer. We can get rid of them. So that means we've either got an 80% decrease or a 20% decrease. And that 80% is super tempting, seeing that 0.80 there. But remember, the base of your exponential is 1 plus a rate, 1 plus r. And if your rate was 80%, that would be 1 plus 0.80, or since it's a decrease, 1 minus 0.80, which doesn't give us 0.80. What gives us 0.80? What value of r? R would have to be, subtract 1 from both sides, r would be negative 0.20, or negative 20%, which would be a 20% decrease. That's the one we want. Move that decimal over a couple places to make it a percent. But we've got a 20% decrease. Pay attention to whether it's increase or decrease. That's about the size of the base. And remember, it's 1 plus the rate. You subtract the 1 to figure out what the actual rate is. All right, here we are switching from radicals to fraction exponents, or fraction exponents to radicals. The main thing to remember is that the denominator of an exponent and the index of the radical, they have the same job. They come from the same place. So when I switch back and forth, I'm switching between having a denominator or having an index. Since there's two things inside this first radical, they should each get a fraction exponent. Both of those fraction exponents, since they're both inside the same cube root, they both get a 3 in the bottom, and they get the exponents they already had for the top. If there was no exponent, they'd get a 1, but they did have an exponent, so they get what was there. Now, we can leave it like that. It just said rewrite it, but maybe you saw that 3 over 3 and decided, hey, I'm going to reduce that, make that y to the 1, or just plain y. So x to the 2/3 y. The second one, slightly harder. It's less going on, but we do have to pay attention to the fact that there is no index. When you don't see an index, well, we can still make a fraction exponent. That 5 still goes on the top. But that invisible index, what is our invisible index? Well, it's the number of things we need inside a square root to get one outside. That's 2. So it's going to be c to the 5 over 2. That's come up more than once, more than 10 times in class. Make sure you remember that no index on it, on the radical, means it's a 2. How about the 5th root of xy squared? Now that squared is outside, and that is worth noting. There are no parentheses in this problem, but because the x and y are both inside the radical and the square is not, it's like there's parentheses around the whole thing. Why does that matter? Well, when I give them each their fraction exponent, yeah, they each get a 5 in the bottom because they're both inside the radical, but they also both get that squared. They both get the 2 on top because it distributes to them. You don't need parentheses for the radical to signify the grouping for us. Well, the bottom problems go the other direction. So k to the 3/4, that 4 is going to become our index, that 3 is going to stay an exponent, and that 3 can go inside or outside the radical, doesn't matter. Now I say doesn't matter, it doesn't matter because there's only one thing inside this radical. Remember, there is a difference when there's two things inside. Now, the second problem runs into the opposite issue. There are no parentheses on this one, which means that the 5 does not get that 2/3 exponent. It doesn't get an exponent at all, so it's not going to be in a radical at all. So it stays outside. The a is the only thing inside the radical. 3 ends up as our index. 2 is an exponent inside or outside. Since it's just an a in there, it doesn't matter. This last one, xy to the 3/2 power, this one is in parentheses. There's two things in there, so I think we need a fraction exponent or an exponent on each one. The fraction's going away because we're writing as a radical, and since they both have that over 2, they both go in a square root. Don't write the 2 in. We don't do that. We keep it invisible. But the x and y each need an exponent, and that's the 3. They both go inside the square root because they're inside the parentheses. They both get a 3 because they're in parentheses. All right, Ramon's record collection is another example of our future value equation. This one does deal with money, but it's not compound interest. So again, we don't have the n's, r over n and the nt. That's only for compound interest. It's a very specific version of this, a little bit more general equation. Now we do still have the r, and it says that the value of his collection increases by 8% annually. The word increases should help us eliminate a couple wrong answers, because we know if it increases, our base of our exponential has to be bigger than 1, which means a and b are both out. Neither one of them has a base bigger than 1. So it's got to be C or D. Now our P in every one of these was the same, was that 12,500, so that wasn't that big a deal. The R is the big deal, and remember it's 1 plus R. So 1 plus 8%. How do we write 8%? We're going to write it as 0.08. Change it into a decimal. What's 1.08? Or what's 1 plus 0.08? 1.08. Now the T is just going to be the X. That's not a big deal. Whenever it says X years, that just means they're replacing the T with the X. But as soon as we got that 1.08, we should have spotted that the answer was C. Be careful, 1.8 is also tempting, but that would be 80%. Make sure you get your decimal moved the right number of places. Number 7 actually looks pretty scary. The area of the base of a cone-shaped pile of sand, B is not the pile of sand, B is the area of the base, is related to S, the amount of sand in the pile, by the formula S equals all that stuff. Which of these are equivalent formulas? Now equivalent, that's a term we've seen come up before with multiple choice and multiple select problems. Equivalent means we can get away with just plugging in a number for the variable and seeing which ones are equal. Now when I say the variable, I'm not talking about S. All of these are equal to S. S doesn't matter. It's V in the formula that we need to plug in for, and we can plug in whatever we want. I'm going to go with 7. And 7 is my favorite thing to plug in. It doesn't matter if you wanted something that seemed more reasonable, 70, 700, something like that, if those worked better for you. But 7 should work fine. If we plug that into our calculators, being very careful to make sure it all gets typed in the way this looks, it's going to be 17.696. And let's try plugging in 7 for each of these. On A is going to give us 80.407. That's not it. B is going to give us 192.938. That's not it. C does work, 17.696. Now the decimals keep going on, but we just rounded to 3. So C is good. How about D? 17.696. We're on a roll. How about E? No, E actually comes out really, really small. That's because our V and our 36 end up in the bottom. The only thing in the top was pi. And then raise that to the third. It's going to be a very small value. So only 2 of these worked, C and D, so only 2 of these were my correct answers. And that is a great way to work this problem. Is it the way they wanted you to work the problem? Probably not. How is it designed to be done, though? Well, the way it's designed to be done, probably to take the radical, and just looking at all these, we've got a lot of fraction exponents. Let's see if we can rewrite this with fraction exponents, which means each thing inside should get a fraction exponent, kind of like the one we were doing a few minutes ago. So that means that each of those things inside should actually end up to a fraction power. Anything that doesn't have an exponent gets a 1 over. So maybe we just put all of it to the 1/3 power, just using some grouping. That's a little sneaky, but it's actually one of the answers. It's exactly what C looks like. Or we could distribute the exponent, as we're more common to do, which means everything gets that 1/3. The 1/3, v to the 2/3, pi to the 1/3. That looks an awful lot like D, but not quite the same. What's the difference? Well, D says 6 to the 2/3. This says 36 to the 1/3. But what is 36? 36 is 6 squared. And if I change out that 36 for a 6 squared, they're equivalent. 6 squared to the 1/3, that's 6 to the 2/3. 6 to the 2 times 1/3. Raising power to a power, you multiply the exponents. That is also an acceptable answer. There's no way to change the original problem to be any of these other things. You're not going to get a 1/2 power like A. You're not going to get a 36 that's not being raised to a fraction power because it does belong inside the radical. You're not going to get a pi on top and all this stuff in the bottom. And again, a square root, you're not going to turn a cube root to a square root. So none of those are going to be right. Those are the two answers we needed. Now, it doesn't matter which way you did it as long as you found the right answers. I hope this helped bring some of this exponent and exponential stuff back to the surface of your mind, especially the future value equations, which are on your formula sheet, so you can look that formula up, and then the fraction exponents. Those are the biggest things we were dealing with on here.